Hey there, welcome to today's Explainer. I am absolutely thrilled you're tuning in. Go ahead and grab a notebook and a pencil, because today I'm putting on my physics teacher hat for a high-yield tutoring session all about wave mechanics. We are going to unpack exactly what sound is, how it travels, and how we actually hear it. By the time we're done here, you are going to be a total master of sonic foundations.
Here's our roadmap for today. We'll be covering sound basics and wave properties, sound reflection and echoes, the biology of the human ear, ultrasound tech, and then we'll wrap the whole thing up with a quick knowledge check.
All right, Section 1, Sound Basics and Wave Properties. Understanding how energy travels through a medium.
Okay, so the absolute foundational rule you need to know is that sound is produced by vibrations, period. And it absolutely requires a material medium to travel. It just cannot exist in a vacuum. No medium, no sound. Now, when sound travels through that medium, it moves as a longitudinal wave. That basically means the particles are moving back and forth, parallel to the direction the energy is traveling. As they do this, they create two distinct zones. On one hand, you've got compressions. These are high-pressure, high-density zones, where particles are literally squeezed together. On the flip side, we have rarefactions, and these are low-pressure, low-density zones, where the particles are spread far apart.
Let's apply this to real life. Think about sound traveling in the air versus sound traveling underwater. Since we just established that sound needs a medium, imagine how those vibrations might act differently depending on what they're moving through. In a gas, like the air around us right now, the particles are pretty spread out. But in a liquid, like water, those particles are packed much closer together. That actually changes how those compressions and rarefactions ripple outward. It's the exact same type of energy transfer, just interacting with a totally different density of particles.
To really nail this for your exam, we've got to speak the mathematical language of sound. Let's break down two critical properties. First up, wavelength. We represent this with the Greek letter lambda. It's simply the distance between two consecutive compressions or two consecutive rarefactions, and we measure it in meters. Next, we have frequency, represented by a lowercase f. This is just the number of oscillations per unit of time, and it's measured in hertz. Oh, and a quick side note, always remember that amplitude, which is the maximum disturbance in the medium, is what actually determines how loud a sound is. Definitely memorize these, because they are the building blocks of wave mechanics.
All right, pens ready? You're definitely going to want to write these down. These are your essential mathematical tools. First is the time period, which is simply the time it takes for one complete oscillation. The formula is T equals 1 divided by F, or frequency. Second is speed, meaning the distance the wave travels per unit of time. That formula is V equals F multiplied by lambda, so frequency times wavelength. Let me slow down and repeat that for you. T equals 1 over F, and V equals F times lambda. Highlight those, seriously, because you're going to need them for our practice quiz at the end. Moving on to Section 2, Sound Reflection and Echoes, how sound bounces back to us. Just like light reflects off a mirror, sound actually reflects off physical surfaces too, and this creates totally different auditory experiences depending on where you are. Picture yourself yelling across a massive canyon. You hear your voice bounce back as a crisp, perfectly distinct reflection. That is an echo. And fun fact, to hear an echo clearly at around 20 degrees Celsius, there has to be a minimum gap of roughly 17.2 meters between you and whatever the sound is bouncing off of. Now, compare that to walking into a large, busy concert hall. The sound kind of persists and blurs together, right? That's because of repeated overlapping reflections bouncing off the walls and ceilings. That lingering, drawn-out sound is what we call reverberation.
Section 3, the human ear and hearing. Translating pressure variations into brain signals.
So, we've covered the physics, but how do our bodies actually capture these waves? Let's trace the journey of a single vibration. Step 1. The outer ear, specifically the part called the pinna, acts basically like a funnel to collect incoming sound waves. Step 2. Those pressure variations travel down your ear canal and smack into the eardrum, making it vibrate. Step 3, and this is absolutely crucial, the middle ear houses 3 tiny bones called the hammer, anvil, and stirrup. These guys act as incredible biological amplifiers, really boosting those incoming vibrations. Finally, step 4. These amplified vibrations hit the inner ear, or cochlea, which basically performs magic. It converts the mechanical vibrations into electrical signals, which then shoot straight up the auditory nerve to your brain. Section 4. Ultrasound in modern technology. Going beyond the limits of human hearing.
The mechanical waves we call sound actually exist on a massive spectrum, way beyond what our ears can handle. The magic number to remember here is 20,000 hertz. We humans have a very specific audible range, spanning from 20 hertz up to 20,000 hertz. Anything below 20 hertz is called infrasonic. Think of the super deep, rumbling sounds made by elephants or whales. But anything above that 20,000 hertz limit, that is called ultrasound. We obviously can't hear it, but animals like dolphins and bats use it naturally all the time. And, more importantly for us, human engineers have harnessed it to build some absolutely incredible tools.
Let's see how this actually translates to modern tech. Because ultrasound frequencies are so incredibly high, they're super useful in medical diagnostics. We rely heavily on these high-frequency waves for procedures like echocardiography and ultrasonography to safely see inside the human body. It's a total game changer. We also use them in industrial cleaning. The high-frequency waves create these microscopic bubbles that can gently scrub delicate parts hidden in extremely hard-to-reach areas. And then, of course, there's navigation.
Which brings us to sonar, sound, navigation, and ranging. This is literally genius. Ships use sonar to figure out the vast, unseen depths of the ocean or to pinpoint underwater objects. But how? Well, they send out an ultrasonic pulse and then calculate the exact amount of time it takes for the echo to return. Because we already know the constant speed of sound in water, we can use that simple return time to calculate exact distances. It's brilliant physics in action.
Section 5. Knowledge check. Practice questions. Time to test your wave mechanics mastery.
All right, time to bring the teacher persona front and center. I really hope you wrote down those key formulas from earlier. Let's do practice question 1. If a sound wave has a frequency of 50 Hz, what is its time period, or T? Think back to the relationship between time period and frequency we just talked about. Remember, they have an inverse relationship.
And the answer is T equals 1 divided by 50, which gives us exactly 0.02 seconds. Excellent job if you remember that T equals 1 over F. That is a totally fundamental calculation you gotta know.
Okay, moving on to practice question 2. If you know the frequency, F, and the wavelength, lambda, of a wave, what formula gives you its speed, V? I gave you a hint earlier that this is essentially the ultimate master equation for wave propagation.
Got it? The answer is V equals F times lambda. Wave speed is just frequency multiplied by wavelength. If you've got those two pieces of the puzzle, you can always figure out exactly how fast that energy is traveling.
Finally, practice question 3. Let's actually put that formula to the test with some real numbers. If an ultrasonic wave has a frequency of 100 Hz and a wavelength of 2 meters, what is its speed? Take a second and just plug those hypothetical numbers directly into the formula you just recalled.
And the final answer is 200 meters per second. You literally just take the 100 hertz, multiply it by the 2 meters, and boom, you've successfully applied the physics formula to find the wave speed. Congratulations, you guys have absolutely crushed the basics of wave mechanics today. As we wrap up this explainer, I just want you to take a second and look around the room you're sitting in. We've just mapped out the invisible, mechanical sound waves that are constantly compressing and rarefying the air right around you. But it kind of leaves you wondering, what other invisible waves are traveling through you right now? Thank you so much for joining me today, and keep exploring the fascinating physics of our world.